Hi there. Today we're going to have a look at two very particular examples of simple harmonic motion because we can use them to model lots and lots and lots of other situations. And those two examples we're going to look at are a spring, or a mass spring system, and a pendulum, or what we call a simple pendulum. We're going to go through a couple of derivations of how to get the time periods of both of the systems, and you'll see the similarities and difference between them. So if we start off straight away with the spring, so if we say we've got a spring suspended from just a ceiling there, so there it is without the mass on, and then let's put a mass on it. Here we go. Oh, it's got very big. There we go. So now that mass, let's say mass M, and that has got longer and also wobblier for some reason. So let's say that we've got this sort of distance here. It's been displaced by x. And then when it's displaced by x, it's also going to have a force in the opposite direction, which is going to be F. And from Hooke's law, assuming the spring obeys Hooke's law, which we always do in these situations, we say F is equal to kx, or technically minus kx, because it's going in the opposite direction. Yeah, let's ignore this weird thing here. Okay, so we know that F is equal to kx. We also know, through my mate Isaac, that F is equal to ma, so the acceleration of that mass on the end is proportional to that force there. So we can equate these two things and have ma is equal to minus kx. Okay. Now, we also know from our other circular motion, simple harmonic motion equations, that acceleration is equal to negative omega squared x. So we could say negative m omega squared x, by substituting with this a, is equal to negative kx. And if we do some cancellation there, so we cancel out these negatives and we cancel out the x on both sides, we have, let's try and stay consistent with our colours, m omega squared is equal to k. Now we'll do a little bit of rearranging there, so let's take the m over to the other side, and then let's substitute in for omega our definition of omega. So let's substitute in omega is equal to 2 pi over t. And that then will give us 2 pi over t all squared is equal to k over m, which then, if I can make some room for, let's get that out of the way. Let's make some room for down the bottom here. We can expand those brackets to give us 4 pi squared over t squared is equal to k over m. And with a little bit more rearranging, taking that t to the other side, we can have t squared is equal to 4 pi squared m over k. And our final, to give it just equal to t, we can square root the whole thing. So that gives us t is equal to 2 pi root m over k, which is this important part down here. If we were going to be doing a practical to measure this or to verify this relationship, then it makes sense for us to, if we're changing, say, the mass of the system, it's a lot easier to change the mass on the end of a spring than to change its spring constant. It probably makes sense for us to be plotting t squared against m, because then if we have our lovely graph here, we have m as our independent on the bottom, t squared at the side, and then we get a lovely straight line, with the gradient of that line being the part of that equation that isn't m, so is 4 pi squared over k. So that gradient would allow us to find the spring constant in a slightly more reliable way than just taking f equals kx values. Okay, so I'm going to move straight into the pendulum, which is a bit more of a difficult one, and I hope I don't make mistakes along the way. So if you see lots of jump cuts because I've edited this, you know what happens. There we go. Told you I'd make mistakes along the way. I'm only human, even though I do physics. So, if we've got a pendulum swinging from a point here, I'm going to really exaggerate the angles. All of this stuff, we're making small angle approximations. I've got a pendulum bob, let's say mass M, not that really matters here, and you'll see why later. And it is swinging at an angle to the vertical of theta here. Okay. Now we're going to consider the forces acting on this, and there are two forces that we really care about. There is rather, the weight of the object, which is mg, and there is the tension, which we can call T for now. And those two are going to, obviously they're not collinear and they're at different angles, they're going to give us a resultant force, where we can do that with a vector triangle. So if we draw our vector triangle, we've got T, I'm going to draw it nice and big, and we've got mg at an angle of theta going directly downwards. So let's put this here, mg going straight down. Let's label T as well. And then those two are going to give us, let's do this with pencils, just make it a little bit smaller. There we go. Those two are going to give us a resultant force in this direction. So adding those vectors and going from the tail of the first one to the tip of the last one. And that's going to give us a resultant force, which is why the pendulum bob is going to be displaced this way, as we know. And it's going to make a journey, I'm going to approximate it as a straight line, because it's at a very small angle. It is an arc, I know it's an arc, you know it's an arc, but we're going to pretend it's a straight line. And then we've also got a right angle in this triangle here, because we've effectively resolved those forces into parallel and perpendicular components to the pendulum string. Now, we can do a little bit of trigonometry to define these values in terms of theta. So this T here is the adjacent side to that theta, which means that is going to be the hypotenuse, mg, times by cosine of theta, so mg cos theta here. And our resultant force is going to be likewise mg times the sine of theta, because it is the opposite side. So now we're going to look at the dimensions of the pendulum itself. So we've got this displacement here, and we're going to call that x, being our displacement. And there's also the length of the pendulum itself, and I'm actually going to take the length where it is at equilibrium, which obviously in a real pendulum its length doesn't change, but because we're approximating it as a triangle here, we have to choose one side or the other. So I'm going to choose this as L. I'm going to do it with an uppercase L, which isn't necessarily traditional, but my lowercase L's are pretty illegible. So we've got this, and so we can redraw this triangle now as some anonymous side there, L here, and X here. And we've still got that same angle theta. Now we can define sine of theta as opposite over hypotenuse, or x over L. So if we then substitute this definition of sine theta into this sine theta here, we can say that the resultant force on the pendulum bob is mg x over L. And we also know Mr. Newton comes along, F equals ma, so we can equate these two. ma is equal to mg x over L. Now we can do a few more things. We can cancel out these m's, and then we can also use our description of a as being equal to negative omega squared x. So we can say negative omega squared x equals g x over L. And then we can do some cancellation here. So what we really have is negative omega squared equals g over L. That's just rewriting the same line again. I haven't done the algebra there. Now let's just move this up a little bit. What we can do now is just a bit of rearranging. hopefully you see similarities with the spring and mass system. So if we do some rearranging here and substituting in, omega is equal to 2 pi over t. So I'm going to say this is negative 4 pi squared over t squared, as we had before. I'm not going to bother doing the brackets this time around, you've seen it once already, is equal to g over L. And a bit of rearranging, we have t squared equals 4 pi squared L over g. I'm going to be a little bit fast and loose with negative signs here. You can prove to yourself where the negative signs come from. And then, if I rearrange that one last time, just taking the square roots of everything, we end up with t is equal to 2 pi root L over g. So if we just make those little comparisons there, we've got 2 pi root m over k for the time period of a mass spring system, and 2 pi root L over g for the time period of a pendulum system. Obviously lots of assumptions made here, but these are two really key equations for specific examples in simple harmonic motion.